Okay, so welcome to the final video for this series. This is on differentiation rules, chapter 3. I start by saying assume that f and g are differentiable functions and that c and n are constants. Then we have the differentiation rules, which you are so familiar with. We have the constant rule, which says that derivative of a constant is just 0. Sum difference rule, derivative of sum or difference is just the sum of the derivatives or difference of the derivatives. Product rule, derivative of the product, we have to be a little more careful. So product of two functions, f and g, is going to be f prime g plus g prime f. Power rule, this one you should be all too familiar with. You just bring the power, the exponent n, down and then subtract 1. So nx to the power of n minus 1. Special case is when n equals 1, as you can see. So that's the simple case when it's just x and derivative is just 1. Quotient rule. You have a ratio, f over g. The derivative is going to be similar to the product rule, f prime g, but minus g prime f. All of this over denominator squared, g squared. Special case is that when f is 1. Chain rule, f of g, derivative of this is f prime composed of g, and you multiply by derivative of the inside, which would just be g. So that's f of g all prime is f prime of g all multiplied by g prime. That's the chain rule. So you see these kind of parallel the limit laws in terms of, when you say the rules back to yourself, it makes sense verbally. So we have constant rules, sum difference rule, product, power, quotient, and chain rules. Chain rule is probably the trickiest of the bunch, but it's also one of the most useful. So those are the basic rules. We make some brief remarks here. Derivative of an exponential function, a to the x, is just a to the x itself, vertically expanded by a factor ln a. Ln a is just a constant. The special case is that when a is equal to e, so we have an exponential, natural exponential. So derivative of e to the x is just e to the x. Derivative of log to the base ax is 1 over ln a x. And the special case is that when we have ln, so in other words, a equals e, so it's log to the base e of x or ln of x, and the derivative of ln is just going to be 1 over x. So third, this one you can look up in your textbook. It's just saying the derivative of ln of an absolute value. I don't think it's stated quite that way in the book, but I thought it was worth stating this rather than just ln of u, and then it's equal to 1 over u times derivative of u over du over dx, derivative of u. The way they state it in the book is kind of, I think, redundant and kind of obvious, but putting the absolute value here just kind of shows you that, okay, yes, chain rule applies. Don't worry about that too much. It's just kind of to get you to see that, okay, yeah, the chain rule is something you need. The limit as x approaches 0 of sine of x over x is 1, and the limit as x approaches 0 of cos x minus 1 over x is 0. These are very handy to remember. And I think in studying the squeeze theorem, these are notorious for popping up in trig-related questions. So questions involving trig and application of squeeze theorem, these tend to come up a lot. So these are just worth noting. I don't think you can use these just without proof. I think you need some kind of statement of where you got this result from if you're going to use them on the test. But I think they're handy to note, at least to convince yourself that, oh, okay, so if you're ever taking this limit here, sine x over x, you know that it does come to something. It is 1, and in this case, cos x minus 1 over x, the limit as x approaches 0 will give 0. Okay. Finally, we have derivatives of inverse trig functions. Those are given on page 214. Again, it's a box of functions, and probably requires some memorization on your part for what derivative is the derivative of what, and so on. Okay. And lastly, if f is an invertible differentiable function, then we can actually differentiate the inverse function as follows by this formula: 1 over f prime at f inverse x, or letting y equal the inverse function f inverse. We have dy over dx is 1 over dx dy. This is really neat because the Leibniz notation actually sort of cleans up some of this notation that we're all too comfortable with. This is actually kind of hard on the eyes. This actually is easier on the eyes, and it actually makes sense. It's as if you were to take the reciprocal of this. It sort of sheds light on why we use the -1 notation here for F inverse, why it's not to be confused with the reciprocal. It seems like a reciprocal, but it's not, kind of thing. So I think Leibniz notation kind of really clears that up, and this is really handy to remember versus I think this. Okay, I think that's all I have to say about that. I think we can just do one example related to this section so that we can have one in there, and then we'll move on to the quick summary of the potential questions. Okay, so you see here in this question, it's question 9 and part A for 5 marks. So it says use differentiation rules to find the first derivative, don't simplify. It says don't simplify because it's quite possible that the first derivative is going to be something messy, and you might think you have to sort of clean up the terms a little bit, but it's advising not to simplify. Okay, so how do we go about this? We're free to use our differentiation rules. Well, we have a quotient, so f prime x is just going to be, using the quotient rule, f prime g. So f prime g minus g prime f over g squared. With the arguments x, I just didn't put them in, but yeah, you know what that is. Okay, so f prime, so if we call this one f, so we're assuming it's of the form f over g. So if this is f, the derivative is 0 plus derivative of this, a to the x. Remember, vertically expand by a factor ln a, so that's ln 3 times itself, 3 to the x. So that's what that is. So 0 plus that. Okay, that's f prime. Multiply this by g. Okay, what's g? G is this function down here. That's 2 plus x squared. Minus g prime f. What is g prime? This is 0 plus 2x, so 2x. Okay, what's f? F is 1 plus 3 to the power of x. Okay, and the denominator is all squared, 2 plus x squared. And what do we have here? Okay, well, it says not to simplify it. So, yeah, so that's the first derivative. So that's good. As easy as that. And in the end of the exam analysis, toward the end of the exam analysis document, I've put one question from the fall 2012 term test that asks you to find the derivative by first principles. And you can easily check your answer with differentiation rules, and you see that it works out quite nicely. But this differentiation is very straightforward. I mean, you know the differentiation rules, then applying them is not tricky at all. You might get into messy situations, but I mean, it says do not simplify, so I mean, that's a gift. Again, it's a gift question.